Okay, so this video is going to be covering two types of probability, independent and dependent events. And our essential question here is going to be, how are the probability of independent and dependent events calculated? So we're going to start off with some independent events. And what this says is that independent events are events that are not affected by previous events. If an event uses replacement, it is an independent event. So these types of events that we are considering are two completely unrelated events. They do not affect each other at all. And when we're dealing with these types of events, the probability of independent events can be found by multiplying the probability of each event together. Okay, so we're going to find the probability of one event, we're going to find the probability of the other event, and then we can just multiply them together, and that'll give us the probability of both of those events occurring together. So let's take a look at example one. You'll see what we're talking about here. It says two dice are rolled. Calculate the probability of the following situations. So the first one says, what's the probability of rolling an even number on one dice and an odd on the other? So first up, probability of just rolling an even number on one of those dice. Well, how many even numbers are there on a dice? There is the 2, the 4, and the 6. So that means that 3 out of the 6 numbers are even. So probability of rolling that even number is just 3 out of 6. Now for the other dice, if we want that odd number, how many odd numbers are there on a dice? Well, there's the 1, the 3, and the 5. That is 3 numbers out of 6 numbers that are odd. So to calculate the total probability of both of these things happening, we will do 3 out of 6 times 3 out of 6. 3 out of 6 times 3 out of 6. Let me multiply those together. Now, my calculator that I'm using automatically reduces things for me. Yours may not. Mine is giving me 1 out of 4 as my simplified fraction, which would be as a percent, 25%. Sometimes you may want to get it as a simplified fraction. Sometimes you may want it as a percent. Both of those are valid ways of writing your answer. Next up says, what's the probability of rolling 2 6s? Well, the probability of rolling 1 6, let's just consider that first of all. There's only 1 6 on my dice out of 6 possible sides. Probability of rolling that other 6, still only 1 6 out of 6 sides. So I'm going to do 1 out of 6 times 1 out of 6, which would be 1 out of 36. That would be the simplified version. And let's find out what that is as a percent. As a percent, that'd be 0.027, which would round to 3%. Not a great chance of rolling 2 6s in a row. C here says, what's the probability of rolling 2 numbers greater than 4? Okay, so just one number greater than 4. How many numbers are there on a dice that are greater than 4? There's only the 5 and the 6, so only 2 out of 6 sides are greater than 4. Now, for that second number that's greater than 4, obviously that would be the same. So we can take those two independent events and multiply them together. So that should be, as a simplified fraction, 2 out of 6 times 2 out of 6. It's giving me 1 out of 9. That's my simplified fraction, and as a percent, that would be about 11%. Okay, so we're done rolling dice. Example 2 says, what is the probability of flipping a coin 3 times and getting heads each time? All right, so just probability of flipping a coin and getting heads. Well, how many sides are heads on the dice? It's just 1/2, right? And that's not going to change. So the second coin's also 1/2, and the third time that I flip it, it's also 1/2. So I'm just going to take all of those individual independent events, find their probabilities, and multiply them together. So 1/2 times 1/2 times 1/2 is 1/8. And 1 out of 8, I think, is 13%. Am I right there? Yes, I am. 13%. Cool. So independent events, just find the individual probabilities and then just multiply them together. Let's go to the inside here, where we got some dependent events. Now, dependent events are events that are affected by previous events. They are affected. And if we see the phrase without replacement, it is a dependent event. Now, it's not going to change how we find the probability. The probability of dependent events can be still found by multiplying the probability of each event together. It's just that the second or the third event are going to be affected by the previous ones. Okay, so dependent events we got to be a little bit more careful about. Let's look at example 3 and you'll see what I'm talking about. This says a sock drawer contains 10 white socks and 8 black socks. 10 white, 8 black. So that does mean that there are 20 socks total. Just going to make a quick note about that. So A says, what is the probability of randomly picking a white sock, then picking another white sock without replacement? Okay, so that first white sock, or that first sock, I guess we'll just, probability of the first one. So when I'm reaching in that drawer and I'm trying to pick a white sock, well, how many white socks are there? There's 10 out of 20, right? We're starting off, half the socks are wet. Now, when I'm going in for the second one, going in the second time, I'm trying to pick another white sock. We are going to assume that after we pick that white sock, we took it out of the drawer and it's no longer in there because I didn't replace it, right? This says without replacement. So I picked a white sock, it's out of the drawer, and now I'm going back in and I want a second one. This time when I'm going in, there are only 9 white socks remaining because one of them's out. I already picked it. And there are only 19 total socks. So when I go to find my probability here, I need to do 10 over 20 times 9 out of 19. So we can see that when we're dealing with dependent events, numbers are going to be changing. Now let me multiply those together. Simplified, I'm getting 9 out of 38. And as a decimal or a percent, that would be right around 24% if I'm rounding to the nearest hundredth. So what's the probability of picking a black sock then another black sock without replacement? Okay. So for the first one here, if I want that black sock, I start off with only 8 out of 20. Oh, and just consider anytime you have a separate problem, just consider everything reset. So those white socks that we picked in part A, they're not still out of the drawer. We're resetting the whole situation. So 8 black socks out of 20 total socks. And then for the second one, when I'm going in, I've only got 7 black socks left out of 19. So this is going to be 8 out of 20 times 7 out of 19. So 8 out of 20 times 7 out of 19. As a simplified fraction, I am getting 14 out of 95. And as a percentage, I'm getting about 15%. And lastly, this says, what is the probability of picking 2 non-matching socks without replacement? Okay, so I either want a black and a white, or I want a white and a black, right? If these are going to be non-matching. So let's just consider the first one here. The first one, it doesn't really matter which we want. Like let's get a white sock first. So that'd be 10 out of 20, right? Now the second one needs to not match the first one. So if my first sock was white, we did the 10 out of 20. Then for the second one, I need it to be black, which would be 8 out of, but I still took 1 sock out, so this would be 8 out of 19. So we'll do 10 out of 20 times 8 out of 19. Let's see what happens here. 10 out of 20 times 8 out of 19. I am getting 4 out of 19, which is 21%. Cool. So that would be that first way. Now that was a white and then a black, right? So the funny thing is that that's not the only way of getting two non-matching socks, right? Because we went white and then black. But we could have done black and then white, right? That would still be non-matching. So there's actually two different ways of doing this. So we're actually going to take that answer and multiply it by 2 to get our final answer of 42%. Because both of those probabilities would be the same. It's just that it could happen two different ways. So we're going to double it at the end. That one was kind of tricky. Now, let's go ahead and see example 4 here. This says, bag of candy has 4 green pieces, 5 red pieces, and 8 yellow pieces. What's the probability of randomly picking a green and 2 yellow pieces without replacement? Okay, so let's start off with the probability of picking the green candy. So a green candy piece is, there's 4 of them. And how many total pieces do we have? We've got 4, 5, and 8. That's 9 plus 8, that's 17. Now let's get a yellow. Now, how many yellow do we have? There's 8 total. When I'm reaching in to grab that candy, I already took a green piece out, right, with that first pick. So now I'm down to 16 total pieces left. Now I'm going back in and I want to get that second yellow piece. So when I'm reaching in that time, I already took 1 yellow piece out, right? I just did that. So now I'm down to 7 yellow. And how many total pieces of candy are in that bag now? Well, I've taken 2 out, so now I'm down to 15. So this is 4 out of 17 times 8 out of 16 times 7 out of 15. So all of those multiplied together let's see here. As a fraction, I am getting 14 out of 255, which would be my simplified answer, but as a percent, that would be right around 5%. Okay, so what are we looking at here? For our last bit here, okay, we got some marbles here. A bag of marbles contains 10 blue, 8 green, 12 red, and yellow, and 5 yellow. So as a total, 10 and 8 is 18, plus 12 is 30, plus 5 is 35 total. So what's the probability of randomly picking 2 blue marbles with replacement? Okay, so probability of blue. We have 10 blue out of 35. Now, when I pick that blue, I replace it. That's what the with replacement means. This means that these are independent events, meaning that we do not have to do any sort of subtracting or anything. I pick a blue, I replace it with another blue. So when I'm going in for that second marble, the probability of picking that blue the second time is still 10 over 35. I didn't go down to 9 blue, 34 total. It just stays the same because I replaced it. So 10 over 35 times 10 over 35 is all I got to do here. Let's see. I am getting 4 over 49, which would be about 8%. What's the probability of randomly picking 2 blue marbles without replacement? Okay, so we're shifting things around here. Now that first blue is still 10 over 35, but getting the second blue, if I'm not replacing it, it goes down to 9 over 34. So we can see the big difference here about independent or dependent, or with replacement, without replacement. So let's see what happens this time round. So this time around, it's 9 over 119. And as a percent, we've gone up to 0.075. So it's still about 8%. So that hasn't really changed much. But we did see that without rounding, it definitely did change. What's the probability of picking 3 non-red marbles without replacement? Okay, 3 non-red marbles. So let's think about this. Non-red means it could be blue, it could be green, it could be yellow. Okay, so non-red. So how many total is that? 10 plus 8 is 18, plus 5 is 23 out of the 35. Without replacement. So the first one is 23 over 35. The second one, though, is going to drop down to 22 over 34. And the third one's going to be 21 over 33. Right, because we're losing one non-red each time. So let's see what happens here. 23 over 35 times 23 over 35 times 23 over 35. As a decimal, or as a percent, oh my. Sorry, as a simplified fraction, can't get that right. I'm getting 12167 over 42,875. And as a percent, I'm looking at about 28%. All right, then for this last one here, the probability of getting 3 blue marbles in a row with replacement, or 3 red marbles without replacement. What's the greater odds? Okay, so the blue marble, how many blue marbles did we have? We had 10 blue marbles. So this is 10 over 35. And if this is with replacement, that means that each time is completely independent of the other ones. So we just need to do 10 over 35 times 10 over 35 times 10 over 35, right? Let's see what happens when we do this. I'm getting 8 out of 343, or about 2%. So this is the 3 blue marbles in a row. Now, the 3 red marbles without replacement. So, probability of getting just 1 red is 12 out of 35. So this is going to be 12 out of 35, but this time it's without replacement, meaning I lose one each time. So that goes down to 11 over 34, down to 10 over 33. So we start off 12 out of 35. Then we go to 11 over 34. Then we go finally to 10 out of 33. And this is giving me 4 out of 119, which is about 3%. So we want, the bigger one is the 3%. So we're going to say that our better chance is for the 3 red marbles. And then last one, example 6 says, what has the greater likelihood of happening? Rolling 2 dice and getting 2 sixes, or flipping a coin 5 times and getting heads each time? All right, now these are completely independent events. We're not losing anything. Rolling a dice isn't going to affect anything. So let's just find the dice first. Rolling 2 dice and getting 2 sixes, that would be 1 out of 6, because there's only one side that is a 6 out of 6 sides, times 1 out of 6 again. That would be 1 out of 36, which I believe we've already done this. That is about 3%. And then the coin, if we flip a coin 5 times and get heads each time, well, how many sides are heads? Just 1 out of 2, right? So I need to do 1 out of 2 times 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 1 out of 2. I need 5 flips there. And I need to do that 5 times. This is 1 out of 32, which would give me about 3%. So let's go to the decimals here. Let's compare these decimals, actually. This was for the 36, 1 out of 36. That was actually 0.027. And our coin was 0.031. So the bigger 3% is certainly the coin. The coin is the winner there. We got a better odds of flipping that coin 5 times and getting heads all 5 times than just rolling 2 dice and getting 2 sixes. I don't know about you, but naturally I would think that the dice have the better chance, but the odds were not in their favor. So your turn to try some things out. You got some marbles to consider, and then you've got some coins and some dice to consider as well. Give those a shot and then come back and finish this video up when you're ready to check your work. All right, probability randomly picking 2 green marbles without replacement. Well, we have 4 green marbles out of, it looks like 20 total. So start off with 4 out of 20. And then we're going back in. We want to pick another green marble. We did not replace it. This was without replacement. So then I'm going to go down to 3 out of 19. Let's see what this looks like. 4 out of 20 times 3 over 19. That is, nope, not 9. Sorry. That is 3 out of 95, which is about 0.03, which would be 3%. So either of these are cool. Picking 2 green marbles with replacement, well, that'd be 4 out of 20 times 4 out of 20, right? If I am replacing it, those numbers don't have to change in that case. This would be as a decimal, or I'm sorry, as a simplified fraction, 1 out of 25, and that is 4%. So better odds of happening if we replace it. Probability picking 3 non-blue marbles without replacement. Non-blue would be the green, the red, and the yellow. That's a 4, a 2, and an 8, that is 14 out of 20. Without replacement means that those are going to go down by 1 each time because I'm not replacing them. So 14 out of 20 times 13 out of 19 times 12 out of 18. That is 91 out of 285, which would be about 32%. All right, and then flipping a coin and rolling a dice. What's the probability of a coin landing on tails? Well, tails is just a 1/2, and a dice landing on an even number. There are 3 even numbers out of 6. So 1/2 times 3/6 would give me 3/12, which is 1/4, which is 25%. And then rolling a number less than 3. Less than 3, that just means it's a 1 or a 2, so that's 2 out of 6. And the probability of landing on heads would, of course, be 1/2. So 2 out of 6 times 1/2 is 2 out of 12, which is 1/6. And 1/6 as a percentage is 17%. Okay, hopefully that went well for y'all. And that's going to wrap up our video on independent and dependent events.